Okay, this is this is a reminder.
Okay, so today we're going to talk about what they call radio wave characteristics. Basically, it's going to be about propagation, primarily for VHF and UHF, since as a technician, that's essentially your operating frequencies, except for 10 meters. And there's a little bit about the 10 and 6 meter VHF stuff. This section, or sub-element, I should say, comprises 3 actual exam questions. So there's like 34 questions that we'll go over, and 3 of those will be on the exam.
Wow.
Somebody's waiting.
Oh. Yes. Good morning, BJ.
Good day. How y'all doing?
All right. We just started, so you didn't really miss anything. Amateur radio is basically utilizing transmission of information by radio waves, which we call electromagnetic waves, because it's composed of an electric and a magnetic field that are orthogonal or at right angles to one another. Primarily, we use the electrostatic part of the wave. And if you see on that little diagram, move this out of my way anyway. The, I guess, kind of salmon color, or whatever you want to call that, is the electric field, or the E field, where the blue is the what we call the H field. And you notice that in this particular case, that E field is oscillating back and forth in the horizontal direction. So we call that horizontal polarization because it's horizontal with respect to the Earth. That's the definition of polarization. If we were to rotate that 90 degrees vertical, then it would be vertically polarized. And your handy talkies, which you'll probably wind up with as a technician, you'll notice it has either a little short stubby antenna on it, or a longer one, which is vertically polarized. And your receiving antenna, whoever you talk to, repeater or another handy talkie user, will also have a vertically polarized antenna, and they must both be vertical.
What do you mean by vertically polarized?
If you look at the little diagram there to the bottom right, and if you were to rotate that so that it says propagation direction, instead of coming down to the bottom right corner, would be going straight up. That means that it would be vertically polarized. The red waveform would be going up and down that antenna in a vertical orientation as opposed to horizontal, which is the way it's shown. We'll talk about that a little more later. I'm just getting ahead a little bit. The basic thing is, remember that the electric field and the magnetic field are 90 degrees apart, or right angles, or orthogonal, however you choose to remember it. And we call them electromagnetic waves because it's composed of both an electric field and a magnetic field. So the first question, what are the two components of a radio wave?
Oh, Charlie.
Charlie.
Okay. What is the relationship between the electric and magnetic fields of an electromagnetic wave? Okay, some of the parameters we need to deal with for an electromagnetic wave. And by the way, light is an electromagnetic wave also, not just radio. Is the frequency, which is the number of complete cycles per second. That's how many times it changes direction from positive to negative. And if you remember in the first couple sessions, we talked about alternating current means that it alternates and changes direction from positive to negative. It must cross zero. Wavelength is kind of related to the period. It's the distance that the wave travels in one complete cycle. Now, depending on the medium, if it's free space, these waves travel at the speed of light, which is approximately 300 million meters per second. It's actually 299.997 something. 300 million meters per second is close enough. And in the formula we'll use, we even round it down to 300 with a little math trick. We use a small c to represent the speed of light in the equations. And in slower media, like wires, coaxial cable, things like that, waves travel at a slower speed. And that speed relative to the speed of light is what we call a velocity factor. So in the case of a normal copper wire, it's about 0.95, which means it's 5% slower than the speed of light in a copper wire. In coax, it's typically in the 75 to 90% range, depending on what the dielectric is. We just had a demo at one of the club meetings the other day. Were you there for the dummy load?
Yeah.
And turns out when you put that insulated wire in water, the velocity factor was, what was it, 0.25, 0.23? Something like that.
I didn't catch what he said. I don't remember what.
It was amazing because water is a very high dielectric. As you increase frequency, okay, it takes more energy. I mean, if you think about it, if you were to wave your hand slowly versus as fast as you can, it obviously takes more energy to wave it as fast as you can. And the same thing's true with generating a radio wave. It takes more energy and it contains more energy the higher the frequency. Also, the higher the frequency, the shorter the wavelength, since it's basically a reciprocal. Okay? If it was 60 cycles, the wavelength is, I'm not going to do the math, but very long. The little chart there kind of shows where things are in the spectrum, where radio waves are down here at kind of the low end. And then we get up into the infrared, visible light, ultraviolet light, X-rays, gamma rays. This will also become important later on when we talk about safety and RF exposure. We have ionizing and non-ionizing radiation, where basically anything in the infrared and lower is non-ionizing. It doesn't change your DNA. I mean, you might get a sunburn, and it does heat, when you get up to the ultraviolet and X-rays and gamma rays, they can actually mess up your DNA and cause death. This is showing wavelength is basically measured from either peak to peak, or you could do it trough to trough on the wave. It's the same. And that would be, if you know how fast is traveling, okay, then that time difference times the speed of it. Oops. So we calculate wavelength with a formula, and we use the symbol lambda. It's a Greek symbol. We tend to use a lot of Greek symbols. So it's the speed of light divided by the frequency. So that would mean it was 300 million divided by the frequency. Well, if we say we're going to use frequency in megahertz, or 10 to the 6th units, then we can say that it's 300 divided by F. Because it's 300 times 10 to the 6th divided by F times 10 to the 6th. So it makes it a very simple formula. And again, the lower the frequency, the longer the wavelength, the higher the frequency, the shorter the wavelength. I highlighted those because it's an exam question. Example, I guess I need to move my box here. The wavelength for a typical 40-meter frequency, which I picked 7.150, it's kind of in the middle of the band there, would come out to 41.95 meters. So if you notice, we call it the 40-meter band, but when you look at the actual frequencies for that band on your band chart, they don't ever come out even with 40. It's an approximation. And likewise, the one below it for the 20-meter band. If you just did 20 meters into 300, you get 15 megahertz. The actual band is in the 14 megahertz and up. Where'd my cursor go? Okay, so what is velocity of a radio wave traveling through free space?
Alpha.
Speed of light. What is the approximate velocity of a radio wave in free space?
Beta.
Beta.
What is the formula for converting frequency to approximate wavelength in meters? (300) divided by the frequency in megahertz. What is the relationship between wavelength and frequency?
It's gonna be Bravo.
Sounds good. Okay. A lot of times you see references to RF or radio frequency. It's kind of a generic term, and it really is a radio signal of any frequency. Technically, 60 cycle AC is RF. It's 60 hertz. We tend to use both frequency and wavelength to refer to a radio signal. We either talk about it as like a 20-meter band frequency or actual megahertz frequency. And like I said before, the radio band in meters is an approximation because it doesn't come out nice with that formula, but it's approximately correct. If you were to look at the 2-meter band, which you'll be able to use, it goes from 144 megahertz to 148 megahertz. So you've got a 4 megahertz band there. And if you took the middle of it, 146 into your 300, you're going to get 2 point something.
Okay, so most of both bands are set up on 2-meter plate.
It depends. It could be dual band, both.
So it's dual band.
Yeah.
Dual band. Yeah.
2 meters and 70 centimeters are the normal handy-talkie and repeater frequencies. We split the RF range up into groups or sub-ranges, they call them, where we have medium frequencies, high frequency, very high frequency, and ultra high frequency. As a technician, you're allowed to operate in the VHF and UHF frequencies. That's goes from 6 meters up through microwaves, essentially. The HF band is primarily for general and extra licensees. However, you can operate on a very small portion of the 10-meter band on single sideband. It's 200 kilohertz wide, I think.
Yeah, it's 10.3 megahertz to 10.5, or 10 meter, 28.3 to 28.5.
All right.
You can operate, but now here's the thing: when you look at the band chart, it specifically says phone, and most of these, well, I won't say most, but many of the radios that you buy that are dual or tri-band plus, because you're like one radio in particular has UHF, VHF, the 2 meter, 70 centimeter, the 220 band. They stick the 220 band in there, or no, they stick 6 meters in there, and then 10 meters. But it's only an FM rig, and it doesn't really say anything about FM on the band chart.
Yeah, actually, does it say single sideband or voice?
I think it says, yeah, I think
If it was
says
voice,
phone.
you could do FM.
So if it says phone, you can do FM.
I think.
Okay, so
I'm not a lawyer, but
yeah, it says single sideband phone. So
okay.
it specifies single sideband.
Okay.
So even though those radios can operate on FM on 10 meters, that's not really in the band plan.
You basically need a base station
You know.
to do the 10 meters. And the medium frequencies, these actually go by factors of 10, where, let me see, HF is 3 megahertz to 30 megahertz. VHF is 30 megahertz to 300 megahertz. UHF is 300 to 3000 or 3 gigahertz. So MF is going to be 300 kilohertz to 3 megahertz.
0.3 megahertz to 3 megahertz.
And there's the band plan we just talked about. This is I think I gave you copies of this for the is one specifically for the technician bands. And you can see all the black, which says you can't operate.
Okay.
And again, this is showing the different sub ranges, which we call medium. We don't do much there. That's kind of down. Well, let's see.
160 is in there, isn't it?
What is 160?
1.5,
yeah.
1.8 megahertz, I think.
So 160 is down there. That's kind of a,
Yeah,
more
160 is
people are operating down in the low 160, but most of your activity is going to be in the HF and VHF, UHF ranges. In addition to frequency, which of the following is used to identify amateur radio bands?
Alpha.
All right. And this down at the bottom, I listed all of the amateur bands. There's quite a few little sections. What frequency range is referred to as HF?
That's a 303,000.
See,
Sure.
Charlie?
I think you're right.
Mhm.
3 to 30. What frequency range is referred to as VHF?
Beta.
Charlie?
I heard a Bravo and a Charlie and a Delta. Well, let's see what it is. It's the next one up. 10 times H.
Oh, very high, not ultra. Mhm.
Right. What frequency range is referred to as UHF?
Delta?
Yeah, they threw a tricky one in here, didn't they?
Yes. Let's see. Yeah, I got it.
But he's waiting to come in your class.
Oh, ooh, oh, okay.
Yeah, that was a tricky one.
Yeah, they do that sometimes. Change the units on you if you don't read close.
Yeah.
The main thing on the exam, read the question carefully, maybe twice. Read every answer before you answer. Because you have the habit of, for some reason, you think you're in a hurry. There's no time limit. And you go down and you find an answer, oh, it's got to be right. And without reading the rest of them, it's usually wrong. What does the abbreviation RF mean?
Mhm.
Alpha?
Yep, just a generic term. Okay, so what all did we learn? That radio waves consist of electric and magnetic fields. Those fields are orthogonal. They're always at right angles. We'll assume that for now. I think actually you can have some phase difference, but that's way beyond what we're going to talk about. We learned that the speed of light is approximately 300 million meters per second. And the formula for calculating wavelength of a electromagnetic wave, the simplified one, is 300 divided by the frequency in megahertz. So you're basically dividing the top and bottom of the formula by 10 to the 6, so they cancel those out. Wavelength decreases as frequency increases and vice versa. Wavelength increases as frequency decreases. We tend to use wavelength, I think, more often to represent the radio bands than we do frequencies. And the various sub frequencies are that we need to deal with are HF, VHF, and UHF. And like the previous question, RF is just a generic referring to any radio wave, even light. Okay.